Okay, welcome everyone to our virtual seminar on time, temperature, and chemical potential in quantum field theory. We have the pleasure today to introduce or to announce David Mateos, who will talk about real-time dynamics of plasma bonds. So please, David, take it away.
Thank you very much, Johannes. I'm assuming that everybody can hear me okay. Otherwise, let me know. This is the first time that I give a virtual seminar in a situation of confinement. So please do interrupt me and ask questions, because this is one of my very few opportunities to talk to adults after being locked at home for 2 weeks now with the kids. And also, I don't have too many slides, so feel free to interrupt anytime. And it's a bit strange for me not to see the audience. So if you ask me a question, please tell me who you are so that at least I know who I'm talking to. Okay, so let me see if I can, yes, here. So as you know, holography maps the quantum dynamics of hot and strongly coupled non-abelian plasmas to the classical dynamics of black hole horizons in asymptotically ADS spaces. And this has been used in the past to obtain very useful insights into the far from equilibrium physics of gauge theories, starting, of course, with the simplest case, which is that of conformal field theories. This is just a list of some references that are relevant. Then also non-conformal theories have been studied, and also theories with phase transitions. However, all of the references that I showed you before fail to or do not incorporate one of the most important properties of QCD, which is the presence of confinement. There are a couple of exceptions, at least, that I will mention in which confinement was included. So I'll mention those in due time. But most of the studies that have been done about the out of equilibrium or far from equilibrium dynamics using holography do not include this property. And this means that the theories that have been studied do not have a gapped and discrete set of asymptotic states like the ones that you might expect in a confining theory. Are there any questions at this point? Okay. So what I would like to do today is to incorporate confinement in the simplest possible setting. There are more elaborate possibilities which are technically harder. So what I want to do is to simply look at the one of the easiest examples in which we can incorporate confinement, and that consists of simply looking at n equals 4 super Yang-Mills compactified on a circle. So if you take this theory, which is a 4-dimensional conformal field theory, and you put it on a circle, first of all, you break conformal invariance because you introduce a scale. And moreover, if you impose anti-periodic boundary conditions around the circle for the fermions, then you break supersymmetry. And at energies below the inverse size of the circle, you get an effective 3-dimensional theory, which is basically pure Yang-Mills, because both the fermions and the scalars acquire a mass because of this SUSY breaking, and because of the boundary conditions. So this theory at distances longer than the size of the circle confines. So we'll take lambda to be 1 over the size of the circle to be our confinement scale. And the nice thing is that we know the holographic dual geometry to this theory, and that's simply the so-called 5-dimensional ADS soliton. This is a geometry which has a boundary that's precisely Minkowski in 3 dimensions times a circle. And it is such that in the interior of the geometry, as you move down in the holographic direction, eventually the circle shrinks to 0 size, smoothly ending the space-time there. And basically the location of this ending of the space is dual to this confinement scale in the gauge theory, because it's telling you that there are no excitations below that scale, as you would expect in a gapped theory. Are there any questions? Okay. Now, if you look at the excitations in this geometry, you discover that they consist of stable normal modes, not quasi-normal, but normal modes. There's no horizon here, so there's no dissipation or absorption. And given the symmetries, you can take them to be, if you ignore the circle or excitations around the circle, so you restrict yourself to the zero mode around the circle, then you can decompose your modes into plane waves in a Minkowski direction of this form, times some radial wave function in the holographic direction. And here the frequency is determined by the dispersion relation as a function of the momentum by solving the corresponding eigenvalue equation in the holographic direction. So at the same time that you determine this radial wave function, you determine this omega as a function of k by requiring that the solutions are normalizable and regular at the bottom. Now, if you introduce temperature and you ask what is the preferred state amongst those that are homogeneous at temperatures below this confinement scale, you discover that that's the ADS Soliton. Whereas if you look at temperatures above the confinement scale, then the preferred state turns into a geometry. It's a homogeneous geometry that has a horizon, so it's just a black brane. And in that case, the horizon ends the space-time before the circle shrinks to zero size. So if you were doing just thermodynamics of homogeneous states at finite temperature in the canonical ensemble, you would discover that there's a phase transition, the so-called Hawking-Page phase transition on the gravity side, between the ADS Soliton geometry and the geometry with the horizon.
So,
however,
so just to clarify, you have the horizon, but not a cutoff explicitly in your geometry.
By a cutoff, you mean a UV cutoff?
Or like, yeah, in the radial direction of
Yeah, no, in the radial direction, I'm not imposing artificially any cutoff. What I'm doing is simply at every temperature, I identify the possible geometries and I look at the one that minimizes the free energy. So if I'm below TC, the one that minimizes the free energy is one that naturally caps off because the circle shrinks. Whereas if I'm above TC, the one that dominates is one in which the horizon is the one that acts as an infrared cutoff, if you like.
Okay, thanks.
Yeah. Now, this is the story for homogeneous states. So infinitely extended states in the Minkowski directions. But if you imagine, oh, sorry, before I go into that, let me mention the first one set of papers that considered actually the dynamics in this ADS Soliton, which mimics confinement. What these authors did was to consider the homogeneous injection of energy into this geometry. So you can turn on a homogeneous source at the boundary, a time-dependent source, which will then inject some energy into the bulk. And because everything is homogeneous, this energy can only do two things. So it will fall towards the bottom. And depending on how large the energy density that you injected is, if it's too little, it will simply bounce off the bottom, go back up, bounce off the boundary, go back down, go back up, etc. And it will keep bouncing back and forth, at least for some time. Whereas if the energy density that you inject is large enough, when this shell, this homogeneous plane of energy, falls towards the bottom, it will then produce a horizon, a homogeneous horizon, and you will end up with a brane geometry like the one I was showing you here. So the reason I'm mentioning this is because we will see a manifestation of this bouncing back and forth between the bottom and the geometry, which is possible because this is to begin with, this is a geometry with no horizon, so energy can just bounce off the bottom and go back to the boundary.
So David, hi, it's Michal. Do you know if this process has or exhibits some qualitative differences from the story of ADS stability, instability?
Very good.
Business?
Yeah, I don't. So I looked at these papers some time ago. I don't remember them discussing this focusing and this, which is eventually responsible for the formation of the black hole in global ADS. And I don't know if this could happen here. I can tell you, well, I can come back to this point later in the context of our work. But in this case, you could imagine that this could happen because everything is homogeneous, so the energy cannot diffuse away in the non-compact directions. So you could imagine that there could be some focusing or some transfer of energy from from long wavelength to short wavelength modes, which eventually could form the horizon after a few iterations of going back and forth. But I don't actually remember if they see that or if they discuss it.
Oh, thanks. Now that I see Ben Krabs there, he also worked on the ADS stability 70 program. So they must have made some statements. I'll just look at the papers. Thanks.
Yep. Okay, so in any case, for the purpose of my talk, what's important is this possibility of bouncing back and forth between the bottom, the infrared bottom, and the boundary. Now, what I discussed so far are the homogeneous states. But if you imagine using this geometry to study the dynamics of collisions, like what we do when we want to use holography to learn about heavy ion collisions, you could imagine colliding two gravitational shock waves or two objects, two lumps of energy, anything you want, at the bottom. And no matter how high the energy that you use to collide these objects, as long as it's finite, you will never form a black brane, because a black brane has an infinite horizon, it has infinite energy. So what you will form is a localized, perhaps very big, but localized nevertheless, black hole sitting at the bottom of the geometry if you collided these objects at the bottom, as you would if you want to collide them in their ground states. So this is the type of object whose dynamics we would like to understand, because it will play a role in any high but finite energy collision that produces a black hole in this geometry. Now, the formation of this localized black hole is dual in the gauge theory to the formation of a so-called plasma ball, which is nothing but a ball or a region of deconfined plasma surrounded by the confining vacuum. Any questions? Okay. So this brings me to a second paper that considered the dynamics in this ADS soliton from 2013 with some of my collaborators, where what we did was to study this type of collisions in the approximation of linearized gravity. What that means is that you simply think of these objects as sources for the gravitational field, or the scalar field if they also couple to other fields. And then you use that stress tensor to as a source for linearized gravity, and then that approximation captures some aspects of the collision, like, as you will see, some particle production, but it doesn't couple, because it's a linearized theory, it doesn't capture the formation of the horizon or its subsequent evolution. But nevertheless, some of the features that we see in our recent nonlinear simulations with Pau Figueres and Hans van Tillen agree where they should with this, where in the region where this is applicable with the linearized gravity description. Now, remember that this theory we are studying has a scale. It's not a conformal field theory, it has a confinement scale lambda. So the physics or the properties of an equilibrium plasma ball are not scale invariant. They depend on the ratio of the total mass of the plasma ball compared to the confinement scale. And on the gravity side, this is quite clear, because if you think about very small plasma balls, meaning that the mass of the plasma ball is much smaller than the confinement scale, this, on the gravity side, corresponds to a very, very small black hole. Small meaning in size, smaller than any other length scale in this geometry. In particular, much smaller than the curvature radius of this geometry. So that means that this black hole behaves like a almost spherical, Schwarzschild-like black hole in ADS, or in flat space, to be precise. So in particular, it has, for example, negative specific heat. This small plasma ball, or the dual of a small plasma ball has negative specific heat. Whereas if you look at large plasma balls, meaning that the mass is much bigger than the confinement scale, which may be what you're interested in looking at if you want to understand the dynamics of heavy ion collisions, because a nucleus has a mass which is much bigger than lambda QCD, because it's, you know, of the order of 200 nucleons. In that case, the dual of the plasma ball is something that's far from spherical. In fact, it looks more like a piece, at least near the center, it looks like a piece of this black brain that I was talking about. So what happens is that as you increase the energy of an equilibrium plasma ball, the horizon goes from something that looks approximately spherical to something that looks approximately pancake-like. Because near the center, it looks like an almost infinite plasma ball, and therefore the horizon looks like an almost infinite black brain. But this, of course, at some point deviates and gives you a finite object. Any questions so far?
Yes, so this is Michael. Could you say why this configuration is stable?
When you say stable, you mean thermodynamically or dynamically?
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 Yes.
Yeah, so dynamically, if you think about it, well, it's actually not obvious that it should be dynamically stable. And in fact, I will come back to this at the end. So in the pure gravity theory, I think these are dynamically stable. Yeah, actually, I'm not 100% sure if they should be. So the answer to your question is that I think it's not obvious that they should be dynamically stable. And in fact, if they aren't, this could actually be a virtue rather than a defect. I'll come back to this at the very end. At this point, I'm not making any claims about whether they are stable or unstable.
Okay, thank you.
Yeah,
David, David, can I make a comment here?
Absolutely.
Hi, that's Pau. So in fact, as David said, when these plasma balls are very small, they are like asymptotically flat Schwarzschild black holes, which we know are stable. So you know that when they are small, they will be stable just by continuity. But as David says, as they become larger and they pancake, then the stability properties could actually change.
Yeah, Pau, even in the, so this is going on a slight tangent, but when they are very small, I agree that locally they look like a small Schwarzschild black hole, but the stability may depend on what boundary conditions you impose at infinity.
I mean, then when they're large, can't you argue that they look like ADS Schwarzschild, which is also stable? I mean, by the same logic.
Yeah, so that's why.
Yeah.
No, I was going to say that in the pure gravity theory, if you just looked at gravity in this idea Soliton, when they are large, I think you're right, Michal, that they are probably stable simply because they look like a piece of a black brain, even though there could be finite volume effects and things like this. But if you couple this to a scalar field, then depending on the potential you introduce for the scalar, this could actually be unstable dynamically.
Yeah, sure.
Yeah, and that is actually something that I'm thinking about, because it could, I'll come back to this at the end, it could be a way of mimicking hadronization. Any other questions? Okay. So what I would like to show you today is the dynamics of small plasma balls. So this is very important to keep in mind because the results that I will show you may or may not apply to large plasma balls, or they may only apply to a certain degree, etc. So we don't yet know what differences there may be in this far from equilibrium dynamics between small and large plasma balls. I think some of the effects are robust and will still be better, but I don't know. I cannot make any precise claims yet. But I think the results we have for the small plasma balls, we are now looking at plasma balls, intermediate sized plasma balls. I think, as you will see, some of the results are already new. So what we're going to do is to consider gravity coupled to a massless scalar field, in this ADS Soliton. So there's no potential for this scalar. And what this means is that in the gauge theory, we started with n equals 4 super Young-Mills. We put it on this, we compactify it on a circle, and we truncate to the sector, which includes only the stress tensor and a scalar operator dual to the scalar field in the bulk. Okay, so it's a marginal operator because the scalar field is massless, and it's a consistent truncation as implied by the fact that on the gravity side, it's consistent to truncate to gravity plus the scalar. So in particular, all the results that I'll show you are not just results for a bottom-up model, but actually you can think of them as really applying to a model that we know how to embed in string theory as n equals 4 super Young-Mills. So what we do is not yet to simulate a collision and then form a horizon from a collision and see what happens. What we'll do today is sort of a prior step to that, but it's almost the same, which is instead of forming the horizon by colliding asymptotic states, what we'll do is we'll simply choose initial data in the bulk appropriately for the scalar field in such a way that initially there is no horizon, but there's this sort of cloud of scalar field which will collapse through gravitational interaction and form a horizon. This horizon is initially far from equilibrium. It's deformed in different directions, in different ways, etc. And it's excited in the holographic direction. And then what we'll see is we'll watch, what we're going to do is to watch how this evolves in time and how it approaches equilibrium at late times. So as I said, we set up these initial conditions, and this is what happens. So what you see, I'm going to show you a video of what happens. This direction here is the holographic direction that I called R. And these directions here are the non-compact X1 and X2 directions in the gauge theory. And I'm suppressing the circle. So this is what happens. What you see here is the scalar field. This is the profile of a contour plot or a color plot of the scalar field evolution in time. Okay.
Sorry, I probably, you probably said it, but I might have missed it. You start with the horizon, right?
No. So
no.
In the video, it looks, so in the simulation, there's at t equals 0, there's no horizon. But there's a configuration of the scalar field which very quickly forms a horizon by collapse.
Oh, okay, thanks.
It's just one way to set up initial conditions that will lead to an out of equilibrium horizon, whose dynamics you want to study. So you could imagine that this horizon is some sort of approximation or model of the horizon you would form if you were to collide asymptotic states, which is something that eventually we want to do. So what you see in that video is that so what you see here, this is the excised region where the black hole is sitting. What you see in the video is two things. You see that the relaxation of the horizon towards equilibrium produces gravitational scalar radiation of two types. One is this radiation that gets propagated to infinity. Remember, these are the x directions in the gauge theory. So you see these wavefronts propagating out, because the idea Soliton acts like a waveguide, okay? Where whenever there's no, away from the horizon, there's no dissipation, so these waves simply propagate out without dissipation to infinity. And as I will show you, this corresponds to particle production. So production of asymptotic states that will propagate to infinity in the gauge theory. And there's also radiation that propagates back and forth between this region at the bottom and the boundary, and then back to the bottom, etc. Okay, if you remember in the video. The intuition behind this, so this is the same type of bouncing back and forth that I mentioned at the beginning in the homogeneous case studied by Ben Krabs and Elias Kiritsis and collaborators. And the intuition here is a little different, precisely because we don't have something homogeneous. We have a horizon which is localized in these x directions. So what's happening is the following. If you look at modes that have wavelengths much longer than the size of the horizon, those ones are not efficiently absorbed by the horizon because they don't fit in the black hole. So those simply disperse to infinity. Those are these waveforms that propagate out. On the other hand, if you have wavelengths much shorter than the size of the horizon, those are extremely efficiently absorbed by the black hole. A black hole absorbs very efficiently anything smaller than its own size. So those very quickly don't bounce back and forth, because the moment that they fall through the horizon, they simply go through and get absorbed. But if you look at wavelengths of some modes with wavelengths comparable to the size of the horizon, those do not disperse away very easily because they are attracted gravitationally towards the black hole, but they are also not very efficiently absorbed because their wavelength is not short enough. So those actually sort of get trapped in a sense in this region, and those are the ones that can bounce back and forth many times before part of them is absorbed and another part is eventually radiated away. Any questions about this?
So yeah, Johannes, so you show this a scalar field. What is, can you associate already to a physical quantity on the QFT side?
Yeah. So even though I'm not going to show you plots of it, the scalar is dual to a scalar operator. And this, from the fall-off of the scalar near the boundary, you can simply read off the expectation value of this operator. What I'll show you, I'm going to focus on the expectation value of the stress tensor, so energy density and pressures, which you read off from the fall-off of the metric at the boundary, but you could do the same thing for the scalar. I'm just choosing to show you the scalar in these plots because it's easier to visualize than because it's just one quantity instead of the metric, which has several components. Okay. So this physics, this bouncing back and forth, can also be seen in the gauge theory. So let me show you a video. What I showed you earlier was a video in the bulk, where you could see the scalar field propagating out to infinity and bouncing back and forth in the bulk. Every time that you get this bounce back and forth in the gauge theory, I'll show you first a video and then some plots. You get some disturbances in the energy density and the pressures. So let me show you a video of the energy density as a function of the position in the gauge theory and as a function of time. Good. So what you see at the center is what you would call the plasma ball, which is going to be left behind once all this radiation, all these ripples propagate out to infinity. This is particle production or particle emission by this plasma ball, which is what will be left behind at the end. So let me show you.
Sorry.
Yeah.
Oh, I guess I just had a question about what you want to say next, so please say it.
Okay, yes. Yeah, so I want to show you in more detail or convince you that indeed these ripples that you see here that get pushed to infinity or emitted to infinity, these ones here, propagate out over here. This truly corresponds to the production of the asymptotic states in this theory that I mentioned at the beginning, that you can compute simply by looking at the spectrum of the Laplacian of some scalar field in the ADS Soliton, for example. So in order to show you that, let's do the following exercise. Take the scalar field that, so what we do is we take the scalar field from our simulation in the bulk. This is a function of time, x, and r, the holographic direction. And what we do is, at different times, we decompose it in this basis of plane waves, e to the I kx, and in this basis of radial modes in the ADS Soliton, which are this psi n of r. So the result of projecting into this is the mode, the corresponding mode amplitude, which is labeled by n and k, and that depends on time. Okay? So here what I'm plotting is these different coefficients, these different projections into the different modes in this basis as a function of time for different n equals 1 or n equals 2, and for different values of k. Okay, just some representative values, k equals 0, k equals 2, etc. So if these modes were already truly the asymptotic states, then this dependence on time would be exactly a sinusoidal dependence with a coefficient, with a frequency, which would be the one determined by the dispersion relation that I mentioned at the beginning. Okay, so you would have that this phi n k is simply e to the I omega n of k times t. Now, you already see in here that this is not yet the case, because even if you go to late times, because there's still some modulation in these amplitudes. Okay, the amplitude should be constant if this is simply an oscillatory function. So let's look at that in a little more detail. What I'm showing you here is precisely a sinusoidal fit to each of these curves, okay, to the black, the blue, and the green curve, where you make the fit in a sliding time window. So for example, if you try to fit this between 0 and 1.6 in this region, okay, you extract, by doing a best fit, you extract a frequency for the black curve, which is in some units, 9.6. If you fit between 0.8 and 2.4, you get 10.4. And if you fit between 1.6 and 3.2, you get 10.5. Okay, for this frequency of these oscillations. And you see that this is, in brackets here, I'm showing you the result for the ADS Soliton, for the truly asymptotic state. And you see that these numbers are seem to be converging for all of them. They seem to approach the correct value. As you would expect at later and later times, that's when you expect that this radiation will decouple, the different modes will decouple from one another. So the fact that this is already showing that, but not quite yet, is telling you that you're approaching freeze out, but you're not there yet. Okay, there are still some nonlinear mode interactions between these different particles, so they haven't decoupled completely from each other, but they are about to decouple, as you see from the fact that their frequencies are approaching the frequencies of the corresponding asymptotic states. Did I answer your question, Michal?
Yeah. I mean, one comment that I may have is that in one of the latest papers, we looked at signal analysis, and we used this Prony method in a similar setting, in a sense that like we're like sliding window and trying to see how things change as we slide window, and it's working extremely well to identify frequencies. So one may try it on these data without doing the fit.
Okay, thanks. Any other questions?
Actually, sorry, one more question. I mean, that's probably the essence of the previous one that I wanted to ask. So shall I think of it as some sort of hadronization, or that's not the right way of thinking about it?
I'll come back to this also at the end. Let me postpone that. It's particle production, but it's not what you would call hadronization, because hadronization is really the conversion of the plasma into hadrons. So I'll come back to this at the end.
Okay, thanks.
Okay. So that's what I wanted to say about I just wanted to show you that the radiation that gets emitted towards infinity is really, you can think of that as particle production. Now let me look at this radiation that bounces back and forth between the bottom and the boundary. So in order to show you that, let me look at the energy density and the pressures at the center of the plasma ball at the boundary as a function of time. So if you plot that, this is what you get. So the black curve, the continuous black curve, is the energy density as a function of time. And actually, before I do that, let me draw your attention to the dashed black curve, which is a bit simpler to understand. This is the energy density as a function of time for a simulation that we did, which has an initial scalar profile, which is too weak to form a horizon. So what it does is simply, it has some non-trivial dynamics, but eventually it all disperses away to infinity. You're left behind with no plasma ball in the center, okay? The reason I'm pointing this out is because that has simpler dynamics than in the case where you form a horizon. And it's easier to see here these periodic disturbances in the energy density. So you see, you get the first pulse here, then it goes basically to 0. Then you get the second pulse because it's when you bounce for the second time, the pulse reaches the boundary. Then it goes to 0 again, it bounces again, and so on and so forth. This is also something that you see in the simulation with the formation of the plasma ball, but it's a bit less clean because not only you have this bouncing back and forth, but you have this non-trivial dynamics and wobbling of the horizon, which makes it a bit less clear. But you can still see that you get these periodic disturbances, etc., in the energy density, and the same is true for the pressures. Any questions about these plots?
Yes. Could you comment, please, on the negative energies?
Yes. Having negative energy when you're far from equilibrium is not a problem. It's something that we have seen before in particular in holographic simulations.
Okay, thank you.
Yeah. Even in a supersymmetric theory, you can have locally, so what's positive definite is the total energy, but the energy density can become negative. And as you're pointing out, that's what happens in the beginning here. Even the black curve goes negative here. Good.
Oh,
yeah.
So sorry, a simple question. So can one, so as far as I understood the setup, like there's this plasma ball, right? And then there's emission of radiation, gravitational waves in the spatial directions on the boundary, right? And then there are like these oscillations of the plasma ball that are triggered by something bouncing back and forth, and partly get absorbed and partly not getting absorbed, sort of on top of the plasma ball residing at the bottom of this solution, right?
Yeah.
Is there some effective description of these oscillations of the plasma ball that you can adopt here?
Yes. Well, I think there should be. So when you are sufficiently close to equilibrium, you should be able to describe this with quasi-normal modes of the plasma ball. And if you have big enough a plasma ball, this will include some hydrodynamic modes.
Okay. And did you try to do this here, or?
We are working on that, but I don't
Okay.
have any results to show you yet. Yeah, no, it's far from trivial. And even computing the quasi-normal modes is something that I think would be extremely interesting because they should interpolate between the quasi-normal modes of a spherical black hole and the quasi-normal modes of the black brain, right? As you change the size of the plasma ball. But technically, they are a little harder to compute than the usual quasi-normal modes because this is a localized object, so you have to solve PDEs, not ODEs, to compute the quasi-normal modes.
So you mean like you would do the Fourier decomposition in the angular variables, but then you would have like the radial dependence in ADS and the radial dependence with respect to the center of the plasma ball.
Exactly.
And the Fourier transform in time as well.
Exactly. So you would have holographic. So dependent. So usually the quasi-normal modes that we compute with Fourier transform in time and x, and they only depend on the radial direction, the holographic direction. But in this case, they depend on holographic direction and the direction away, the radius in the gauge theory, away from the center of the plasma ball.
Wouldn't these methods that Roberto and Paran was developing for like interesting black hole solutions apply here as well for plasma balls? Like these black fold approaches.
So the black fold applies when you have a separation of scales. Which may be the case for very, very large plasma balls. But in that case, I think what's gonna give you is that what you will learn is that the quasi-normal modes of these very large plasma balls approach those of an infinite black brane.
Yeah, sure. So that's not the most interesting region.
So I think, no, well, it would still be interesting to see how you interpolate between one thing and the other, right? But
yeah, sure.
Yeah. So I think it's a very interesting problem, but it's a bit harder than just the usual quasi-normal modes that we compute. Yeah.
Sure, thanks.
Yeah. Good. And also, I think even more interesting than that is the question about hydrodynamics. Yeah. Good. Okay, so now let me show you that at late times, this plasma ball seems to settle down to an equilibrium plasma ball, which has a temperature about 2.1 TC. Remember that this is supposed to be a small plasma ball. Small plasma balls have negative specific heat, which means that as the energy of the plasma ball goes down, the temperature goes up. So the fact that this settles down to a plasma ball with temperature above TC is consistent with the fact that it's a small plasma ball. Very good. So this is a plot of the energy density of the profile in space of the energy density for this plasma ball at different times. These are snapshots at different times. And what you see is that at the earliest time, the energy density doesn't show much structure. It's just this profile here. Whereas if you wait a little bit, that's when all the short wavelength features of the scalar field at the bottom that we set up to form the horizon reach the boundary. And that's when you get this blue curve here, okay, which has these now ripples and so on. And then this thing evolves in time and you get these different snapshots. And the latest one here, this one in black, is this one. And the one in black but dashed is the one corresponding to an equilibrium plasma ball at temperature 2.1 TC. And you see that in the middle, they are sort of close to one another, but as you go out away from the center of the plasma ball, they deviate more. And that's simply because this late time that I'm showing you here is still not late enough for this plasma ball to have settled down completely to equilibrium. Another way to see this is to look at the anisotropy, the local anisotropy at each point in the plasma ball. And what I mean by that is you go to some point away from the center, in particular, of the plasma ball, and you look at the local rest frame at that point, and you compute the two pressures. There are two pressures because there are two non-compact directions. And then you plot the difference between these two pressures as a function of the position away from the center of the plasma ball. And what you see, of course, is that this is very large at early times. And as time goes by, this anisotropy decreases, but it's still large. And by that, I mean large compared to the local energy density. Because, for example, even if you look at the latest time shown here, that's the black curve, you see that, for example, of course, at the center of the plasma ball by symmetry, this anisotropy is very small. But if you go out to, for example, x of order 0.4, you see that this difference in pressures in units of the confinement scale is about 2. And you should compare that with the energy density divided by 3 at that point and at that time. And if you go to this plot, you see that the energy density around there is, let's say, 6 or 7 or 8. Okay, you have to divide that by 3. So you get again 2 or 3, which is comparable to the difference in pressures. Okay, so the anisotropy is order 1. That's what I'm saying. Away from the center, even at late times. So that's telling you that you haven't reached equilibrium yet. And in particular, the system has not isotropized. Any questions about this plot? Okay. Good. So let me then, I'm moving towards the end, and I want to make a few comments, and in particular, come back to this issue with the hadronization. So the first comment is that these bounces back and forth, which are a consequence, direct consequence of confinement, because they only happen because outside the horizon, you have a confining vacuum, which is able to reflect this energy that's coming down back up. So the presence of these bounces lead to an equilibration time, which is longer than what you would have expected if you didn't have them. Okay, because they produce these periodic disturbances that prevent the plasma ball from settling down completely to equilibrium at early times. Now, in the gauge theory, this dynamics corresponds to 2 things. It corresponds when the energy is traveling from the bottom to the boundary. That corresponds to a transfer of energy in the plasma ball from infrared modes to UV modes, from long wavelength to short wavelength modes. And when it reaches the boundary, it produces this wobbling, these deformations in the shape of the plasma ball, which is then coupled to this transfer of energy between infrared and UV. So it's 2 different phenomena taking place in the gauge theory, which here corresponds to simply this thing bouncing back and forth from the horizon to or from the bottom to the boundary. Now, one of the things that I'm interested in seeing is how this, if in any way, is modified for large plasma balls. Because for large plasma balls, if you have a very large plasma ball and you look away from the edges towards the center, this is very good at absorbing radiation. So it may be that these disturbances only happen near the edges, or at least mostly near the edges. So this is something that remains to be seen. I don't know yet to what extent the dynamics of large plasma balls will be very similar, or only a little bit similar to these small plasma balls. So this is something to keep in mind. And now let me come to the possible differences between what I have described, which is the dynamics of an infinite n theory. So a gauge theory with gauge group SUN with n going to infinity in the planar limit, because I'm using gravity to describe it, and a finite n theory, which is what we would like to understand. So suppose that I do this collision. I do a collision to form this excited plasma ball in both cases. So initially, in both cases, you expect that you will form a very deformed horizon. So initially, the plasma ball has some size, and you will form some excited horizon in the holographic direction. If you then evolve this system in time, as I showed you, one of the things that happens as the horizon falls towards the bottom and becomes bigger in the gauge theory directions, which corresponds to the plasma ball expanding and cooling down, one of the things that happens is that this system radiates anything that it can radiate, in particular the scalar field in this case, and gravitational waves in the bulk. Now, one main difference between finite n and infinite n is that this radiation at infinite n carries no entropy at leading order, because the entropy of this radiation is order 1, or it's actually on the gravity side at leading order, it's 0, because it's a coherent field, classical field. But more precisely, you should think of it as order 1 compared to the order nc² entropy that's sitting in the plasma ball because of the presence of the horizon. So this separation, this hierarchy, which happens at infinite n, is of course not there at finite n. At finite n, this carries an entropy of order 1 compared to the entropy in here. But in any case, in both cases, you can understand this radiation as particle production. It's just that these particles carry very little entropy at large n. But more importantly, if you now think about what will happen at later times, at finite n, you know that once the plasma ball has cooled down and expanded enough, it will hadronize. It means that all this energy density and this entropy sitting in this region will then get, in this deconfined medium, will get transformed into hadrons, pions, protons, neutrons, etc., that you will then detect at the horizon, at your detectors. Whereas at infinite n, the description of this system is just classical gravity, and you know that in classical gravity, the horizon cannot just disappear, it cannot even break up, okay, it cannot pinch off. So what's going to happen at infinite n is that when the plasma ball has reached a scale, a thickness of order lambda, it will then simply, instead of keeping the expansion, it will simply wobble back and forth until it settles down to an equilibrium plasma ball. Okay? So that's a main difference, because it means that the final state at asymptotically late times at finite n is a bunch of hadrons, whereas at infinite n is some plasma ball, some equilibrium plasma ball sitting at the center, which still has most of the entropy. Okay. Turning this, so of course, if you were to include quantum corrections in the bulk, what would happen is that this plasma ball eventually would Hawking evaporate. And that Hawking evaporation would correspond to the hadronization. Okay, it will produce gauge singlets, which will take away then the entropy and the energy density. And at sufficiently late times, again, what you would find is just a bunch of hadrons at infinity. But Hawking evaporation is suppressed at infinite n, and that's why there you only have this classical description in which you end up with a plasma ball. Nevertheless, as I showed you earlier, confinement effects appear already at early times, and this may be similar at infinite n and at finite n. We don't know that. So there may be, despite this difference, this potential difference in the asymptotically late time state, there may be interesting things to learn about the effects of confinement in the far from equilibrium dynamics of gauge theories. And also, it may even be possible to model hadronization holographically, for example, using instabilities, coming back to the stability of the plasma ball. If it turns out that this plasma ball, when it becomes cold enough, becomes unstable, you could imagine that even though classically you cannot describe the breakup of the horizon, that's actually what you would want to do if it's dynamically unstable. So there may be a way of using that to model the transformation of the big plasma ball into a bunch of very little black holes that you may want to think as little hadrons or things like this. Okay, if you're interested, I can try to elaborate more on this. I don't have any specific results, but it's something that I have thought about a little bit. Thank you.
Thank you very much for this very clear talk. It's not easy to get applause online, but at least a bit here. So we have time for questions now. So please speak up if you want to ask something. Maybe let me start right away out of curiosity. So David, what is like the computational cost for simulations of that kind that you presented?
It's high. I mean, for that you probably want to get an answer from Pau or from Hans, but these are simulations that run on a supercomputer.
Yeah, we were, for the lowest resolutions, we were running at 128 cores. For the highest ones, you'd require maybe 4 times more than that. And in fact, our latest times were essentially computational cost.
Yeah.
So yeah, are there further questions?
Yes. What do you expect if you would reduce the coupling? I guess you have infinite coupling if you're using this ADS-CFT setup. Can you guess something that happens if you use some Gauss-Bonnet term or something to reduce the coupling strength?
My first reaction is to say that I don't think qualitatively much would change, because the way I think about so we make 2 approximations when we use classical gravity to describe the gauge theory. One is infinite coupling and the other one is infinite N. The fact that we have large coupling basically means that we cannot describe asymptotic freedom, which is also a very important property of QCD. But I don't think that's the most important property. Once this plasma ball, so for example, one of the things that we don't have is when you collide these objects, because we don't have weak coupling, you don't have things like jets or anything like that. But the dynamics of the plasma ball itself, I don't think should be qualitatively too different if you include finite coupling corrections, as long as you're still close to infinite coupling. But I have to say that I haven't thought very carefully about it.
Thank you.
Mm-hmm.
I have a question. So if one think about this plasma ball as deconfined matter that you create in heavy ion collisions, like over here you have this additional effect in which the energy gets carried away by particles, right? Is there a lesson for a similar effect in heavy ion collisions, or like this is something that there is relevant, or how do you think of it?
Well, in heavy ion collisions, this certainly happens because when you collide these 2 nuclei, you certainly produce at the end a bunch of hadrons, and some of those hadrons come from early times, so to speak. So this radiation that I've been describing here, in a way, you could think of as the first burst of particles that will reach the detector before most of the plasma ball has expanded and hadronized.
So can you try to turn your findings into some sort of a qualitative lesson? In the sense that some percentage of the energy is lost in this way.
Actually, I think that's not where I would put the weight. I think if there is some lesson, but as I was emphasizing, we have to see what happens for large plasma balls, is in this, I think the most robust effect is this bouncing back and forth of the energy density, which means that this is both a confinement and a finite volume effect. So given that the plasma ball that we form in heavy ion collisions is certainly in a confining theory and it has finite volume, there may be some qualitative lesson to be learned, I think, from this. But I think it's a bit early yet to say which.
Well, that's interesting. Thanks. Sorry, I hear silence. I have one more question. So when you think about finite volume effects, like, is there some sort of, and maybe it's completely inappropriate, but some notion of a surface tension for this object? In the sense that, like, there's a bulk medium, right? But there's also a boundary of this medium to, like, what happened, I mean, you know, a plasma ball and the rest of the world, right?
Yes. Let me see. Yeah, there is a surface tension. Yes, you could, if you have a very large plasma ball, for example, then what you will see is that there's a region in the center where the energy density is basically constant and equal to the energy density of a black brane at T equals Tc. And then if you go very, very far away from the plasma ball, the energy density will go to 0 because it will go to some, yeah, let's say to 0, because what you have is the confining vacuum. So there will be an interface that will interpolate between these two regions. And that interface is something to which you can assign a surface tension. It's basically a localized transition between the two phases, and that you can basically assign a surface tension.
So when you calculate the quasi-normal modes, like you would get information about the medium, but there would probably be also some effect coming from this boundary, right?
Yeah, although the reason I'm hesitating to make very strong statements is because that boundary is, so let me just take a step back. The reason I'm hesitating is the following. So in the bulk, it looks like there's a very sharp transition between the region where you have the, if I go back here to this picture, sorry. Here. So the transition between this region where it looks like a black brane and this region where there's a confining vacuum, here is very sharp because at some point the horizon literally ends. So here you have horizon, here you have no horizon, okay? But if you actually compute the energy density, the expectation value of the stress tensor at the boundary, what you get is simply an exponential fall off. But the energy density never really goes to 0. It just dies off exponentially over here. So it's not a very sharp interface in that sense. So the system will have some quasi-normal modes, but I'm not sure to what extent you will be able to separate that between dynamics of this bulk region and dynamics of the interface.
Oh, sure, you're right. I mean, like sharp features in the infrared of ADS translate into something that is moving out at infinity. Yeah.
Yeah, because this thing, what you're doing basically is you're computing a shadow of this at the boundary, and that smooths out the sharp interface.
Yeah, sure. Thanks.
Yeah.
Hi, it's Christian. I also have a question. Do you know if this bouncing back and forth between the horizon and the boundary still would happen if you give the scalar field a mass?
Yeah, for sure it will happen, because even though I was focusing on the scalar field, well, I think, yeah, no matter what the mass of the scalar field is, as long as it's, as long as the, so I'm assuming the scalar field does not destroy the boundary conditions, meaning that it's dual to a relevant or marginal operator.
Mm-hmm.
It will still propagate information from the bottom to the boundary and back. This is simply a geometric property of this geometry. And the same is true with the gravitational field. Even though I didn't show it, the disturbances you see in the energy density are precisely because the metric is bouncing back and forth. And that will always be there.
Okay, thanks.
Yeah.
Okay, it seems that there are no further questions. So then let's thank David again.